One of the really big questions right now in particle physics is really to find out what dark matter actually might be. We fundamentally know how much ordinary stuff, so the stuff you and I are made out of, is in the universe. And we know it's about only 1/5 of the stuff we can see in gravitational interactions. Since we have really no clue what dark matter is supposed to be, and being not very good with names, we call it dark matter. If you imagine you have a detector which weighs 1 gram, and you have a detector which is 1 billion grams, then it's clear that the detector which weighs 1 billion grams should have 1 billion times the dark matter interactions per unit time than the 1 gram one. But if you now change the unit of time over which I observe and say I'll take 1 gram and observe that for 1 billion years, then it's going to have the same probability for dark matter interactions than 1 billion grams in 1 year. The problem now is that the typical grad student doesn't want to hang around for 1 billion years. Neither does the typical faculty or anybody else. And so the question is, how can you detect an interaction in a detector which happened 1 billion years ago? The only thing on this planet which is 1 billion years old are rocks, okay, minerals. So you have to basically go and try to find a way to look for evidence of dark matter in rocks or minerals. And that's what we're trying to do. It's called mineral detection of dark matter. And the idea is, while most of the energy deposited by dark matter interaction happens in the form of ionization or heat, so fleeting things which go away immediately, and if you don't see them in the moment it happens, you just haven't seen it. A tiny fraction of the energy also changes the makeup, the atomic makeup of the crystal structure of the mineral. The simplest one you can imagine, you have this very regular arrangement of atoms inside a crystal, and dark matter comes and just knocks out one of these atoms out of the crystal. So now the crystal is missing one atom in a place where you know there should be one. We try to find this whole pattern which would be indicative of dark matter interaction in a rock. And for that we're building this microscope. It turns out that this type of technology has some real-world applications. So one of our sponsors is the National Nuclear Security Administration, and they're not very interested in dark matter, but they're very interested in people doing dark things with nuclear energy production. Specifically, they're worried about the nuclear proliferation. This is where this really goes from very sort of curiosity-driven research to very applied things. I also should say that these holes in crystals play an important role in nuclear energy production. What limits the lifetime of a nuclear reactor is essentially how long the steel vessel holding the thing together can survive the neutron bombardment. And that is all related to holes in the crystal structure of the iron making up the vessel. With this technology, we can also help people to better understand where these defects are coming from, how they formed, maybe to design materials which can better withstand irradiation. And especially if you think about AI, data centers, and this renewed interest in nuclear energy, finding materials which can deal with high neutron doses becomes, of course, much more important than it used to be.